Hi there, welcome to your lesson on sampling and presenting data. We are moving into the world of statistics now. Let's get rolling here. Let's begin. Basically the journey we'll take in this lesson is first we'll discuss types of data, then we'll talk about gathering data, which is known as sampling, and then presenting data. So that's the typical process somebody will take: considering data, gathering the data, and then presenting. Okay, so let's begin with types of data. So two main types of data are univariate versus bivariate data. Univariate data has only one variable. For example, let's say we collected some data like this, and we have these values. Maybe they represent the ages of people in a building. All right, so it's only one variable. We've only collected data about their age. We can present univariate data in different ways. One example is presented as a box and whisker plot, which shows a low value, high value, a median, and so on. All right, bivariate data is data that has two variables. For example, here we collected data about students, and we collected two variables about them: their classwork grade and their final grade in a course, let's say, or final exam grade. And then bivariate data, a very common way to look at it is to plot it as a scatter plot and look for correlation. So bivariate means two variables, univariate one variable. All right, so again, bivariate data, two variables, univariate one variable. And with bivariate data, you have data on different variables collected from the same individuals, and you want to compare them, for example, in a correlation analysis. All right, a little bit more about data. So there's also something known as qualitative data. So bivariate and univariate data can be now these classifications. So qualitative data is descriptive, such as eye color, hair color, favorite TV show, etc. Quantitative data has to do with numerical data. It's numerical data. Quantitative comes from quantity. For example, shoe size, weight, these are all things that are measured by numbers. Quantitative data is split into two types: discrete and continuous. Discrete data is data that can be counted, or in other words, it's data that can only take on particular values. For example, shoe size. Shoe sizes come in, I guess, in whole number values or half sizes perhaps as well. Or number of people, for example. If you say how many people is there in a room, there can be 5 or 6 or 7 or 20 or 30. You can't have half people. Continuous data, in contrast, is data that can be measured. It is data that can occupy any value within a continuous range. For example, weight, height, temperature. If we say we want to get the weight of people, we can say, well, lowest weight, let's say, is 10 kilograms and highest is 80 kilograms. And somebody's weight can be any number in between, any decimal fraction number in between. That's continuous data. All right, looking at this list, we have some examples. Discrete data, again, can be counted or it can take on certain values. So here's some discrete data. Number of pages in a book, right? It has to be discrete. Continuous data, it can be measured or take on any value. So length of a string, the length of something can be measured, so that's continuous. You can give that to any degree of accuracy. Shoe size is discrete. For example, here's some shoe sizes. Temperature is continuous because, again, you can measure temperature, and when you can measure something, you can give it to any degree of accuracy. Example 3 for discrete is people in a race. How many people are in a race? That's discrete. It can only take on certain values. However, the time taken to run a race is something that can be measured. Time can be measured. Therefore, it's a continuous variable because we can measure it to any degree of accuracy. So on this one here, I want you to decide on all of these here, which are discrete, which are continuous. Try it now. All right, hope you did okay with that. Let's recap some things again here. So we have discrete and continuous data. Discrete data is either data that can be counted, for example, the number of cars in the car park, or data that can only take specific values, for example, shoe size. We've talked about that. Continuous data can be measured, for example, height, weight, time. Okay, here's a little reflection on that. Is the taxiing speed, so that's the speed that an airplane is going down a runway, is the taxiing speed of an airplane discrete or continuous? All right, and now is the number of airplanes waiting to take off discrete or continuous? Hopefully you came up with continuous for the first one and discrete for the second. Now, could data ever be classified as both discrete and continuous? What do you think? Well, the answer to that is no. And let's think of this kind of situation. Here's an example I have for you. A lawyer is paid by the hour. Okay, so even if they work 1 hour and 1 minute, they can charge their client for 2 hours. So therefore, when logging hours billed to a client, a lawyer may enter 0 hours, 1, 2, 3, etc. They enter whole numbers. So that looks like discrete data. However, it's not. It looks discrete, but the variable we're measuring there is time. And time measured in hours can be measured to any degree of accuracy. 5.3 hours, 6.24 hours, 7.344 hours. You can quantify that data in any value between a max and a min. Therefore, it is continuous. Important to consider. All right, now let's talk about population sampling. So let's say we have a population. That's the whole group of people or objects or whatever that you want to get statistics or data about. When we have a population, we often don't look at the whole population. We just take a sample of it. It means a part of the population, and we say that sample can represent the whole. That's what sampling is all about. Let's talk about that now. So when collecting data, students often ask, how many data items should I have? There is no fixed value, but you need to ensure you collect enough data so your results are reliable and are representative. That means they represent the whole population. So to recap those ideas, a population consists of every member in the group that you want to find out about, whereas a sample is a subset of the population that will give you information about the population as a whole. When we talk about reliability of data, data is reliable if you can repeat the data collection process and obtain similar results. That's an interesting definition, right? So if you take one sample from a population and then you say, okay, now I've learned something about the population, then you repeat, take a different sample, and the new sample gives you similar conclusions about the population, then you know your original sample has been reliable. Okay, data also needs to be sufficient when you're collecting data. So reliable and sufficient. Data is sufficient if there is enough data available to support your conclusions. So that has to do with, do you have enough data, and do you have enough data to speak about the whole population? All right, so about reliability of data, there are two main factors that contribute to the unreliability of data. They are missing data. This means perhaps from a lack of responses in surveys or questionnaires, or from an ability to collect specific data. Sorry, I guess I should say from an inability to collect specific data. And the other cause of unreliable data is errors in handling data. Maybe there's improper collection of the data, the tools are incorrect, or the survey is not a good survey, or you have incorrect summarizing or aggregating of the data. So once the data is collected, something in the process of collecting that data into a different form is wrong. Okay, so now we can also come across sampling bias, because we're talking about taking a sample from a population in order to represent the whole population. So we can have bias. Our sampling technique might be biased, and this means when you take a sample, some members of the population are more or less likely to be selected than others. When you select a sample, it should feel random. It should not feel planned. So that would be bias. So there are things called sampling techniques which help us avoid bias in samples. So in order to produce an unbiased sample, there are a number of established sampling methods which statisticians have developed. The best method for any given scenario will depend on what information you want to find out. The combination of two or more sampling techniques can be used for your best sample. Let's take a look at sampling techniques now. So what we're going to do now is, rather than reading these, I'm going to have you pause the video each time, read the description or the definition of each type of sampling, read the example, and then present your own example that would use this kind of sampling. So read this now and then give your own example of convenience sampling. Okay, now let's look at simple random sampling. Read this, read the example, come up with your own example of simple random sampling. Next one, we have systematic sampling. So again, read the definition here, read the example, come up with your own example of systematic sampling. And now we are at stratified sampling. This one's getting a little more complex. Read the definition, read the example, and then come up with your own example as well. And the final type of common types of sampling techniques is called quota sampling. So read this definition, this example, consider the diagram here as well, and then give your own example as well. Great, you have learned all about sampling, and again, it is your choice which sampling technique you use depending on what you're trying to do, what kind of data you're trying to collect, and what you're going to do with that data. So make sure you always have those in mind when you're collecting data. All right, now we are on the third part of this lesson. We started with what is data, what kind of data do we have, sampling techniques, which means how do we gather data, and now how do we present data. So there's many ways to present data, and you can see some of them here: pie charts, graphs, charts, tables, etc. But we're going to focus now on tables and and basically what are called histograms. So let's take a look. Here are bar charts and histograms. You should be familiar with both of these already. Let's show the main differences between the two. A histogram, you can see this is a bar graph, this is a histogram. A histogram has no gaps. You can see there's no gaps between the bars here. And the reason for that is because a histogram typically represents continuous data. And if you have continuous data, it means that every value is possible. So the bars are, by being connected like this, show that every value is possible. Whereas on a bar chart, it does not have to represent continuous data. So you can see here, it's presenting actually qualitative data here, and there's just a bar above each of these qualitative categories, and they would not be connected. It's not continuous. Okay, next, the horizontal axis on a histogram has a continuous scale. Well, that's what we just talked about. But the horizontal axis in the bar chart has discrete values. We can see that, or categories. We can see that here. Now, for a bar chart, the width of each bar does not matter. For a histogram, the width does matter, because the width represents a certain range of values here. So for example, this bar represents the people that are aged maybe from 60 to 65, or 60 to just under 65, and then this next one would be 65 to just under 70, and then 70 to just under 75, and so on and so on. Okay, that's some important things to know about bar graphs and histograms. Let's keep going. A hint we have for you is a bar chart is suitable for discrete data and may have gaps, whereas a histogram is suitable for continuous data, and there are no gaps. So consider that if you're collecting data and have to represent it. Okay, next, when you have raw data, which can be primary or secondary data that you have collected, a frequency table is an easy way to view or represent your data and look for patterns. Okay, so here's a frequency table. Let's say we have a retail situation where this table shows the ages of people who entered a store. And we can see from 1 to 10 we had 5 people enter, from 11 to 20 we had 8 people, and so on. So here's just tallies, which is a count, and here's frequency. Frequency means a count. It's a number that represents how many times this thing has occurred, all right? So 20, for example, people aged 41 to 50 have entered the store. So frequency table, again, tells us the number of items. Now we can take a frequency table and represent it as a histogram or a bar chart. Here we see a histogram, and we can see again 1 to 10, 11 to 20, 21 to 30, and so on, and the number of people. Here, frequency will always be on the vertical axis, the dependent variable. Notice there's no bars, no space between the bars, and then the intervals are all equal, so the bars all have equal width. So that's a good histogram. But the thing is this truly a histogram? I guess. Is this axis truly continuous? Well, it is. Ages can fall in any value between that. Even though ages are usually given in whole numbers, discrete values, an age can be measured to any degree of accuracy. Therefore, it is a continuous variable, and it does make sense on this axis then as a continuous variable, and therefore a histogram. Look at this example together. We have these scores people earned on a test score, 32 student scores, maximum mark 10, and you can see all the marks here. We're going to collect this in a frequency table. So here's a frequency table for that. We can see the possible score on the test and the frequency values. For example, 6 students earned a score of 7, 4 students earned a score of 8. Okay, that can be then transferred onto a bar or histogram. Would this be a bar chart or histogram? Well, it would be a bar chart because this is discrete data, right? You cannot have scores in between 0 and 1 and so on. You can only have those exact scores. This is discrete data, therefore we have a bar chart showing that. Okay, this is a bar chart, not a histogram. Important. So now let's contrast that with another example. But before the example, let's talk about skew. When you have histograms, you can have skew. This one is negatively or left skewed, because there's like a tail in that direction. This one is positively or right skewed. And this is called a normal distribution. You can pause if you want to read this a little more. Okay, last example here then. We have 37 teachers. They were asked how much time in minutes they spent eating lunch at school. Here are the data collected. You can see some teachers only spent a minute. Others spent up to 16 minutes. That's not much. Please construct a frequency table for this data using these classes. That means these are going to be your categories. You're going to group all the things between 0 and up to including 4 minutes in one group, and then 4 to all the way up to including 8 minutes in another part of the table, and so on. So what are the values in your table going to be? Okay, double check your work. Here's your table. You can see 8, 12, 10, and 7. Notice here, because this is 0 to 4, including 4, if you see a value 4, it's included in this first class, so that would be included here. Whereas here, you would not include 4, you would only have 8 included, so 5 and all the way up to 8. check your work carefully. This is a histogram. Great job. Everything's connected here.